Chapter 7, Reactions in Aqueous Solutions. So 3 general categories of reactions. First thing we're going to look at is a precipitation reaction, and that is when you mix 2 aqueous solutions together to form a solid. It's also known as a double displacement reaction because the positively charged things will switch places as well as the negatively charged things. Acid-base reactions come from reacting an acid with a base. This is also called neutralization, and one of the products is water. Oxidation-reduction reactions occur when there is a transfer of electrons. Generally speaking, these are single replacement reactions, and we will also look at a couple others. So first thing we have to do is define what we're talking about in terms of solutions. So a solution is a homogeneous mixture, and that means that the composition is the same throughout. So if you take a small sample of it, it's going to have the same components as the larger solution. The solvent is the substance that is doing the dissolving. So solvent means you are dissolving, dissolvent. So the solvent dissolves. It is the component in the solution that exists in a higher amount. So the solute then is the substance that is being dissolved. So the solute goes into the solvent. We measure concentrations in terms of how much solute is present. So aqueous solutions are when the solvent is water, hence aqueous, aqua, meaning water. So aqueous solutions come from mixing a solute and a solvent when the solvent is water. And there are other types of solutions. For example, well, this happens to be an aqueous solution, but in a soft drink, water is your solvent, and then sugar and carbon dioxide are your solutes, among others. You can have a solution that is gaseous, which is air. The solvent is nitrogen, because the air that we breathe is about 79% nitrogen. The solutes are oxygen, argon, methane gas. There's also CO2, some other random gases as well. We can also have a solid solution. If you've ever soldered anything, solvent is lead, and the solute is tin, and there are varying compositions when you solder. So these are all solutions because the sample is the same composition as the whole. So if you take a soft drink from your 2-liter and pour it into a glass, it has the same composition as what is remaining in the 2-liter bottle. So you're not just getting something where you're just going to have water, or you just get a bunch of sugar, or you just get the caffeine or the CO2. So it's all mixed together. Solutions are homogeneous, meaning the same throughout. So here we have 2 aqueous solutions of potassium permanganate. This one is a more concentrated solution because it has a darker color. Potassium permanganate is purple crystal, and dissolved in water, it turns the solution purple. So this solution has been diluted, which means that we have a higher amount of water, a higher amount of our solvent. Here there is more solute. So we can look at electrolytic properties, and electrolytic simply means the ability to conduct electricity. If you're an electrolyte, it means that you can carry a current in a solution. And the way that this happens is through dissociation, which simply means that there are bonds that are being broken during the process of dissolving a solute. The result of this dissociation then is called ionization, because when the bond is broken, we're left with 2 different molecules then. One is a cation, one is an anion. And it is those charges on those molecules then that allows us to transfer the electrons. We're not transferring electrons in compounds, we're just allowing the electrical current to flow through the solution. So here we have an example of a strong electrolyte, lights up the bulb very brightly. Here we have a weak electrolyte, which means not as much dissociation, so we have a dim light. And here, a non-electrolyte, there's no dissociation, so there are no ions, so the electrical current is not being conducted. So let's take a look at electrolytes in further detail. So an electrolyte, or simply a strong electrolyte, is going to be a substance that can dissociate when put into water and forms ions. So there is complete dissociation. The sodium chloride does not remain as a compound when we put it into water. It completely breaks apart into sodium cations and chloride anions. A non-electrolyte is something that will not dissociate. Generally speaking, these are molecules. So covalently bound atoms together are not going to dissociate. Here, when we have ionic interactions, it's more likely that we will see complete dissociation. So when we put glucose into water, it stays together. It's still glucose, but it's dissolved, so now it's an aqueous solution. However, because there is no dissociation, there is no ions, or there are no ions, so therefore the current is not conducted. A weak electrolyte generally comes from weak acids and weak bases, or ionic compounds that are only slightly soluble in water. And the way we know something is a weak electrolyte, we see this back and forth arrow, and for those of you who are going to take chemistry 2, this is going to show up. This is an equilibrium, which means that we're reacting in the forward direction and at the same time reacting in the reverse direction. So this is acetic acid. It is a weak acid. So there is an incomplete dissociation here. Only a few protons come off of the acetic acid. So therefore, we are only allowed to conduct the current in a very minute fashion. So if we look back at the last slide, the strong electrolyte glows brightly with that light bulb because there's complete dissociation into ions. The non-electrolyte, where light bulb doesn't glow at all, results from having a substance in the water that is not going to dissociate at all. Weak electrolytes only weak acids, slightly soluble ionic compounds. So there's only a few of these that come off, hence why the light bulb only glows dimly. So into the reactions. So the first reaction we're going to study is a precipitation reaction. And once again, this comes from mixing 2 aqueous solutions and forming a solid upon mixing. So I have a solution here of sodium iodide. Here there is a solution of lead 2 nitrate. I mix these 2 solutions together, and what ends up happening is I form an insoluble compound, which is lead iodide. So that is the yellow solid that is being formed. And we call these precipitation reactions because the solid, as it is formed, it falls down to the bottom of the beaker. Just like when the weatherman says there's going to be precipitation, either rain or snow or whatever it may be, it falls from the sky to the earth. So we see precipitation because we're forming a solid and it will fall to the bottom and settle. Hydration results from when water molecules will arrange themselves to surround particular ions in solution. So the polarity of water is that it is polar. The hydrogen atoms are slightly positive. The oxygen atoms are slightly negative. So water will arrange itself in a way to surround a negatively charged ion with all of the positive protons or positive hydrogens. We also see then that the slightly negative oxygens can surround a positively charged ion. So this kind of helps shield and separate. But we see then that the water will actually disperse and the negatives and positives can come together. And there are rules that govern what substances will be able to form a precipitate. But hydration is simply looking at the fact that water molecules will surround ions in solution and basically form what we call a solvent cage. So it boxes in those ions to help stabilize them. Because if you have something that's positive and you have something that's negative, it's really not stable. They're going to want to come together in some way. Or if the positives and negatives aren't going to come together and form a compound, they still have to become lower in energy. They still have to be stabilized. So in looking at a precipitation reaction, this is the reaction that was shown in the previous slide. Lead 2 nitrate plus sodium iodide yields lead 2 iodide and sodium nitrate. So how do we figure out? And as I had said earlier, this is a double displacement reaction. We can see that lead started with nitrate, but it ends with iodine. Excuse me, sodium started with iodine, but now it ends with nitrate. So it's like two couples show up to a party, but they leave with other people, which is not very cool. So we switch partners, and one of the compounds potentially can form a precipitate. This here is what we call a molecular equation because we have everything in its correct formula. Everything is together, nothing is dissociated. Here we have an ionic equation, and the ionic equation results from the fact that if you have something that has an AQ, which stands for aqueous, that means that this substance actually exists in its ionic form. So lead exists as lead 2 plus, and NO3 exists as the NO3 minus, as nitrate. So these have charges. Same thing here. This is aqueous. So sodium iodide dissociates to form ions, the sodium plus and the I minus. Over here, because we have a solid, we cannot separate that. That is together. It is not floating around as ions in solution. But we see here that the sodium nitrate is aqueous, which means these two guys have dissociated and now exist in their ionic form. So we have an ionic equation. Why? Because we have ions represented. And these are all still aqueous. All of your charged particles here are aqueous. They're dissolved in water. The solid is not dissolved in water. So when we look at this ionic equation, we can actually cancel out like terms on either side of the arrow. Since I have 2 nitrates here, they cancel with the 2 nitrates here. I have 2 sodium atoms, 2 sodium ions going in. I have 2 sodium ions coming out. So they cancel out. So what I'm left with then is what we call our net ionic equation. And when we write our net ionic equation, we really should have our states of matter listed here. So this should be aqueous, this should be aqueous. And what it is the ions that are coming together will always have to equal whatever precipitate is being formed. I have 1 lead atom, I have 2 I atoms. I have 1 lead ion forming together with 2 iodide ions. So this is our net ionic equation. And then we label the sodium and the nitrate as spectator ions. They're called spectator ions because they're not actually participating in the reaction. Just like if you go to a football game, you're there, you're not playing the game, you are a spectator, but you're still present. So really it's the job of the spectator ions to bring the other ions to the party so that they can react. So sodium brings iodine, nitrate brings lead, so that lead and iodine can come together and form an insoluble solid. Insoluble meaning it does not dissolve in water, it stays together. 2 distinct states, so it is not aqueous. We are not forming a solution. Remember, solutions have to be homogeneous. So when we write our net ionic equations, the first thing that we have to do is make sure that we have the correct chemical formulas and that that equation is balanced. We write the ionic equation by dissociating all aqueous substances into their respective ions, and we have to make sure that we have the correct charges on our ions. And if we see something, for example, if I go back here, if I see something like this with the parentheses, this means that for every one of these that I have, I get 1 lead ion and 2 nitrate ions. So I'm not dissociating this like I have 2 N's and 6 O's. The nitrate still stays together. It is a polyatomic. So if I were to have coefficients in the front of this balanced equation, as I do here, this means that I have 2 sodium ions, which I see down here, and I distribute it as well because I see that I have 2 iodide ions when this dissociates. Since I have 2 molecules, I get double the amount of atoms that come out of it. So I write my ionic equation with the correct charges, only separating those substances that are aqueous. Once I've done that, I should have 2 different ions that are spectator ions, one that's positive, one that's negative. and they have to be in the same amount. If I have 2 sodiums on one side, I have to have the 2 sodiums on the other side. If I had 3 nitrates, I'd have to have 3 nitrates. If I had 4 chloride ions, I'd have to have 4 chloride ions. So they have to match, both in their chemical formula and the number and the charge. So I guess that's not a both, that's a 3. Once we cancel out the spectator ions, we're left with the net ionic equation, and we should make sure then that the charges and the number of the atoms are all balanced out. And recall that whatever ions are in the ionic equation, the net ionic equation, they have to be able to form that precipitate. They have to be able to form that solid. So when you're writing out net ionic equations, your final equation has to have a solid as a product. That's it. There's a solid as a product. There are 2 ions, positively charged, negatively charged, on the reactant side, and those are aqueous. So if I was to write out the net ionic equation for the reaction of silver nitrate with sodium chloride, the first thing that you're going to do is check to see that it's balanced. Silver, silver, sodium, sodium, 1 NO3, 1 NO3, 1 chloride, 1 chloride. So we have a balanced equation. Oops, sorry. So we have this balanced equation, which then means that I'm going to separate out the aqueous components. I get a silver plus an NO3 minus, plus an Na plus a Cl minus. This stays together. I have an Na plus and an NO3 minus. So if I write that out, I'm going to see that I have an NO3 minus on this side and NO3 minus on this side that are aqueous. They are ions, so I can cancel them out. I would also see that I have a sodium ion on this side and a sodium ion on this side. Those will cancel out, leaving us with our net ionic equation of Ag plus, that is aqueous, plus Cl minus, which is aqueous, to leave us with silver chloride solid. Ionic equation, once again, is aqueous plus Cl minus, aqueous, yields AgCl, which is solid. The Na plus and the NO3 minus are your spectator ions. So there's going to be a pattern that develops. The solid that is on the right side of the equation, you have to have these respective ions on the left side of the equation. The substance that comes out aqueous as a product, these are your spectator ions. So you simply have to separate those and put them into their correct respective charges. So here's some examples of some precipitation reactions. So we formed some insoluble compounds here, which means that if it is insoluble, it gets a little letter S for solid. If something is soluble, we write AQ for aqueous because it's part of the solution. So here we have some cadmium sulfide, lead sulfide, nickel hydroxide, nickel 2 hydroxide, and aluminum hydroxide. So these precipitates all resulted from mixing 2 aqueous solutions, and now we are going to form these respective solids. So there are rules and guidelines to predict if something is soluble or not. I have a handout that I will give to you in class. So water-soluble compounds, and this is the biggest one or the best one I would say that will always tell us. If you don't have your sheet on you, if you see any group 1 metals or the ammonium ion, that substance is always going to be soluble. Always, 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 always. Now we see here, there's also some anions, which will always be water soluble. Nitrate, chlorate, and acetate. Now, generally speaking, the halides, except for F-, are soluble unless they are mixed with silver, mercury 2, or lead. Oh, that's mercury 1. Silver, mercury 1, or lead 2. Sulfate, generally soluble unless we have silver, mercury, lead, I'm guessing there's some other there. Sorry, those are covered up. Mostly heavy metals. When we have heavy metals, they are not going to be very soluble. Down here, I can look at this, and if I see carbonate, phosphate, chromate, or sulfide, generally these are going to be insoluble compounds. And the only exception is if we have group 1 metals or ammonia. Same thing here. Hydroxides. Generally speaking, metal hydroxides are not soluble unless they're with group 1 metals. We also have barium here. Barium hydroxide actually is a strong base. Or if we see these compounds with ammonium. So the way that we read these tables is, hey, I'm always soluble if I've got this. Are there exceptions? There aren't exceptions to these first two rules. Here, always soluble unless they are combined with one of these metals. Here, sulfate is soluble unless it is combined with some of these metals. And like I say, I'm going to give you a table. There's a table in your book to show you soluble compounds, insoluble compounds. One second on this. So using this solubility table is going to allow us to predict when we do that double displacement reaction, when things are switching partners. Metal A with non-metal B is going to switch, and then non-metal A will be with metal A. So we're switching partners, okay? And once we've switched our partners, we have to use these solubility rules in order to predict whether the compound that is newly formed is going to be aqueous because it is soluble, or if it is going to be a solid because it is insoluble. All right, on to acid-base properties. So, acid-base reactions. First thing, an acid generally tastes sour, which is why citrus fruit has that kind of bitter, sour taste to it because of the acids that's in there, citric acid, ascorbic acid, etc. So we have sour. We also have bitter. Bases taste bitter. Soap, if you've ever had to have your mouth washed out with soap, it tastes very bitter. Both acids and bases will cause color changes in plant dyes. This is true also for any type of acid-base indicators. Will cause a color change. Acids react with certain metals to form hydrogen. Bases feel slippery, like as in soap. Acids will also react with carbonates and bicarbonates to make carbon dioxide. And our aqueous solutions for either acids or bases will conduct electricity. And this is irregardless of whether they are strong acids or weak acids or strong bases or weak bases. They will all conduct electricity. So some definitions here. Arrhenius versus Bronsted. And Bronstet's abbreviated for Bronsted-Lowry. So an Arrhenius acid is an acid that is going to increase the concentration of protons in solution. And when I say proton, I mean H+. So anytime I refer to a proton from here on out, I am talking about the hydrogen plus ion, the hydrogen cation. H+ is a proton. So Arrhenius acids increase the concentration of H+'s. A Bronsted acid is a compound that when it is in solution will donate a proton. So it's going to donate a proton. It is a proton donor. And the thing about Arrhenius acids and bases is that they have to be in water. So Bronsted acid, once again, is a proton donor. And sometimes these definitions will be the same for a particular compound. So for example, hydrochloric, this is acid, water yields, this is called the hydronium ion, plus the chloride ion. So what happened here? The hydronium ion is actually a hydrated proton. If I take H plus H2O, I end up with H3O plus. So here's my proton that's just been hydrated with water. So HCl to water. I notice that on the flip side here, the chlorine is all by itself. It lost the proton. Where did the proton go? The proton went to water. So hydrochloric acid is our proton donor, which then means water is our proton acceptor. We've increased the amount of protons in solution. So this, by definition, hydrochloric acid is both an Arrhenius acid and a Bronsted acid. So Arrhenius acids increase the concentration of H+, and Arrhenius base will increase the concentration of your hydroxide ion. So the OH- becomes greater when a base has been introduced to water. A Bronsted base is just the opposite of a Bronsted acid. Since the acid is donating the proton, the base accepts the proton. So a Bronsted base is a proton acceptor. If I look down here at this equation, first thing I'm going to note is that I have these back and forth arrows, which means a small dissociation, not a complete dissociation. When I have an arrow only pointing in one direction, that means that these two things will completely react to form these two things. So here I have ammonia plus water gives me the ammonium ion and a hydroxide ion. So ammonia to ammonium. I can see that I started with 3 hydrogens, I've ended with 4, which means that ammonia accepted a proton. Water then lost the proton because it donated it to the ammonia. The result of losing the proton leaves water with only an O and an H and a negative charge. So ammonia is my base. Water here is my acid. So anytime you're doing acid-base reactions, you always have to have an acid and a base. Here I have acid plus base. Why? Because water here was my proton acceptor. Why? Because H2O to H3O, I notice that I've increased the number of hydrogens here. So when looking at acid-base reactions, we can simply count protons, count the number of hydrogens of what you start with, what you end with. If you end with 1 less proton, it means that you were an acid in the beginning. If you end with 1 extra proton, that means that you were a base in the beginning. And you're always going to end up with acid base equals another acid base. Well, not always, most often. So here we have a list of strong acids and strong bases. You will need to memorize these. So we have ClBrI, so some of the halogens. Actually, HF is a weak acid. And then we have our nitrate, chlorate, perchlorate, and sulfate. Notice acids all have protons. They all have hydrogens here. Your strong bases are going to be soluble metal hydroxides. So first thing we notice is that we have all group 1 metals here. So if you are a group 1 metal hydroxide, you're a strong base. And then we have some from group 2, calcium, strontium, and barium. So the bigger ones. There's not as much of a strong lattice energy between these. Some more things to talk about with acids. We have monoprotic acids, which mono meaning 1, protic protons, 1 proton. So hydrochloric acid has the ability to donate 1 proton. It's monoprotic. And it is a strong electrolyte because it is a strong acid. We also see that nitric acid donates 1 proton. It's monoprotic. It's a strong electrolyte and strong acid. Now here we have acetic acid, which is not a strong acid. It is a weak acid. Therefore, it is a weak electrolyte. Once again, I know this because I have the back and forth arrows, which means this dissociates to form these two, but then these two can get back together to form our original compound. Hydrochloric acid and nitric acid are strong acids because there is an arrow only pointing towards the product, which means that there is a complete dissociation. Once we have formed these 2 ions, they will never get back together again. Diprotic. Sure, you can guess. Di meaning 2. So these are acids that have 2 protons to donate. Sulfuric acid is a strong electrolyte, strong acid. If we take the HSO4- that results to dissociate the second proton, we actually see that it is a weak acid. Triprotic. Tri meaning 3. So we have 3 protons that can be donated in phosphoric acid, but each of these are weak acids and therefore weak electrolytes. So double arrow, once again, double arrow tells me that this is weak. I can only dissociate a single proton at a time because I only have the capability of reacting 1 proton with 1 base, etc. So I can donate 1 thing at a time. That's it. These do not all happen together. I do not start with H3PO4 and in one single reaction end up with 3 H pluses and a PO4 3 minus. So these are stepwise dissociations. Same thing up here. These are stepwise dissociations. And it gets significantly harder to dissociate each resulting proton. So we have to know how to name acids. If we have a binary acid, which simply means I have hydrogen and only 1 other type of nonmetal, so no oxygens are present, then I simply add hydro in the front and change the ending to -ic. And as I stated here, oxygen and nitrogen are exceptions. Why? Because hydrogen and oxygen form water, hydrogen and nitrogen form ammonia, water is neutral, ammonia is a base. So once I've added my hydro, changed the ending to -ic, I simply say acid at the end. So HCl is hydrochloric acid. HBr, hydrobromic acid. H2S, I only have hydrogen and sulfur, so I say hydrosulfuric acid. Oxyacids, oxy meaning there are oxygens present along with another nonmetal. So generally speaking, these are our polyatomic anions, and we've added an appropriate number of protons to balance out the charge. What do I mean by that? If it's NO3 minus, we only need 1 proton because 1 minus and 1 plus cancel each other out. If I have the sulfite ion, that's SO3 2 minus. I have 2 negative charges, so I need 2 positive charges, which means 2 protons. So I'd have H2SO3. And we saw in the last slide, phosphoric acid was H3PO4. Why? Because phosphate has a -3 charge, so it needs to pick up 3 positively charged protons. So with our naming, if the polyatomic ion ends in -ate, the ending becomes -ic. If it were to end in -ite, it then becomes -us. So the difference between sulfate and sulfite, if it becomes an acid, we say sulfuric acid when it's sulfate. We say sulfurous acid when it was sulfite. So what are the reactions here that we see? Acid-base, we're going to do a neutralization reaction. And the things that are actually coming together are going to be the hydronium ion, because putting an acid into water will create hydronium ions. And once again, that's the H3O plus ion. Putting a base into water results in having hydroxide ions, which once again is the OH minus. So hydronium plus hydroxide yields water. So we have an acid plus a base gives us salt and water. So by definition, a salt is the resulting compound from an acid-base neutralization reaction. So when somebody says salt, I know generally speaking, if we say salt, we're talking about sodium chloride. I want to put some salt on my French fries. But all salts, by definition, are resulting compounds from an acid-base reaction. So here I have a strong acid, hydrochloric acid, plus sodium hydroxide. Aqueous, which means both of these substances dissociate completely. And once again, we see switching of partners. Hydrogen started with chlorine, now it's going to end up with a negative thing over here. Sodium started with hydroxide, it's going to end up with a negative thing over here. So when we're switching, and this rule is for precipitation reactions as well, positives have to go with negatives, and negatives have to go with positives. So I'm not going to form a compound where I have sodium plus and H plus coming together. They would repel each other. So I've done my double displacement. I've switched partners. I now have sodium with chlorine and hydrogen with hydroxide, or a proton, I should say. It's positively charged. So my result is sodium chloride, which is aqueous. I know this is aqueous compound because I can go back to my solubility rules and see that since sodium is a group 1 metal, it's always soluble. Sometimes we have acid-base reactions, which are also precipitation reactions. So I have my sodium chloride and I have my water. Acid plus base gives me salt plus water. Here I have my ionic equation showing the dissociation and the ionization of our reactants. And now I have my my net ionic equation, which shows me what is really happening. Sodium brought hydroxide to the party, chloride brought the proton to the party, so that the proton and the hydroxide could get together and form water. Wasn't that nice of them? Okay, so last type of reaction that we're going to study is oxidation-reduction reactions. And in the name, it implies that there has to be oxidation and there has to be reduction. These have to happen at the same time. And the reason for this is the fact that oxidation-reduction reactions result in a transfer of electrons. So the electrons have to start somewhere and they have to end somewhere. We've actually kind of looked at these already. We didn't know that this was what was happening, but in forming ionic compounds, there is a transfer of electrons. So if you start with elements, as we do here, magnesium and oxygen, we can form magnesium oxide. This is a combustion reaction because we're burning stuff. Initially starting, magnesium doesn't have a charge on it because it's in its elemental form. It's what I like to call a standalone metal because it's not bonded to anything else. It stands alone. Oxygen is diatomic in nature. It is in its elemental form, so it has a charge of 0. But once we've come together to form this ionic compound, we see that magnesium now has a 2+ charge and oxygen has the 2- charge. Well, how did this happen? We know that the metal had to give up its electrons and the nonmetal had to accept the electrons. So we have a balanced equation here. And this is oxidation. So when something gives up electrons, which means electrons are a product, we label that as oxidation. We also look to see that the substance, the reactant, has actually increased its charge once it's formed the product. So I started here with 0. I went up to +2. Now, we don't always have to start at 0. We could have started with 2+ and maybe ended with 4+, but we still see an increase in the charge. So oxidation, generally we see it with metals, but by definition, oxidation is losing electrons. It is also increasing your positive charge. Conversely, we have our nonmetal accepting electrons, so we say it is reduced, or this is the reduction reaction. So in a reduction, we see that the electrons are going to be on the reactant side. So reactant, reduction, electrons, the R's match up. And we also see that we are decreasing our charge. So here we started at 0, here we end at -2. So we've gone down in charge. But once again, we don't have to start at 0. We could say start at a -2 and end at a -3. That's still reduction because we've decreased our charge. So in this oxidation-reduction reaction, we notice 4 electrons are coming off of magnesium, and they equal the 4 electrons that are going in for oxygen. These have to be balanced, and we'll see later in this chapter how we can balance out oxidation-reduction reactions. So overall, if I put these 2 reactions together, I call these half reactions because it's only half of what's going on. If I put them together by grouping all of my reactants on the left side of the arrow and all of my products on the right side of the arrow, I then see that I can cancel out my electrons as if they're spectator ions, but they're not, but they're simply the same on both sides, so I can cancel them out. And then I form my compound of magnesium oxide. I've got 2 magnesium ions with 2 oxygen ions coming together to form magnesium oxide. And we always want to make sure that our final equation is balanced, which it is: 2 Mgs, 2 Mgs, 2 Os, 2 Os. So writing out redox equations, we can also talk about reducing agents and oxidizing agents. So once again here, if I just come down here first, oxidation is a loss of electrons, increase in charge. Reduction is a gain of electrons, and therefore a reduction in charge. Okay, we're reducing the charge there. We're becoming more negative, becoming more positive, becoming more negative. So the reducing agent is actually going to be the thing that is oxidized. So if you yourself are oxidized, that means that you are losing electrons, which means that you have the power to reduce the other substance, meaning you can force the other thing to take your electrons. Hence, you are the reducing agent. Oxidizing agent, then, is the substance that is reduced itself. So these are opposites of each other. Oxidized, reducing agent. Reduction or reduced means that I'm the oxidizing agent. So since reduction means that I'm gaining electrons, that means I'm forcing the other thing to give up the electrons if I'm the oxidizing agent. So the agent is the power that you have to do to the other substance. So we can never be oxidized and the oxidizing agent at the same time, because that means you're forcing yourself to give up your own electrons and accept them at the same time, and that doesn't make any sense. So how can we figure out then what substance is being reduced and what substance is being oxidized? We have to look at what we call oxidation numbers, and this is not really too new to us because we've been doing this already when we were looking at assigning charges for things and forming their ionic compounds. So if I look at this equation, I can figure out my charges based on either I've memorized charges or I have my periodic table. So once again, zinc is a standalone metal here. It's not bonded to anything, it's in its, so it has a charge of 0. Copper sulfate, well, I know that the charge on sulfate is a -2. That means copper has to be a +2 here. Zinc, now that it's bonded with sulfate, SO4 still has a -2 charge. That means zinc has a +2 charge. And then copper, once again, I see a standalone metal, so it is a charge of 0. So when I look at this then, I have 0, +2, +2, 0. Copper went from a +2 to a 0, so it is reduced. Zinc went from a 0 to a +2, so it is oxidized. I can perform the same thing down here, and notice this is a single displacement reaction because zinc kicked copper out and replaced it. Here, copper kicked silver out to replace it in the compound. So standalone metal, 0. Silver is a +1 charge because it can always be +1. Nitrate, -1. Copper, I see now I have 2 of these, or sorry, I have 2 nitrates at a -1 charge, which means my copper is a +2. And silver is a standalone metal, so it's 0. Copper started at 0, it went to 2+. 0 to +2 is an increase in my positivity. Therefore, I lost electrons. Therefore, I'm oxidized. Silver went from a +1 to a 0. Therefore, I gained electrons because my charge was reduced. So I always have to have something in the reaction that is oxidized and something that is reduced. And a little helpful tidbit to remember, the difference between oxidation and reduction is the saying, Leo the lion goes grr, where Leo, L-E-O, stands for lose electrons oxidized. Grr stands for G-E-R, which is gain electrons reduced. So Leo the lion goes grr. So assigning oxidation numbers, there's rules in your book, but I'm going to go through some of these now. Excuse me. So in the first line here, diatomic oxygen, nickel standalone, diatomic bromine, cobalt stands alone. So anytime we are in our elemental states, we always have a charge of 0, always. Line 2 here, I have magnesium oxide, I have sodium bromide. Notice all of these here are main group elements, so we can simply go off of our periodic table and what we talked about with groups 1 through 8A, right? All of our main group elements, our S block and our P block, follow specific rules and say these are only going to have 1 charge. They are based on their group number because that tells us those are the number of valence electrons the substance is going to give up or to gain. Line 3 here, I see different compounds all containing hydrogen. In this here, I see hydrogens with nonmetals. And in that instance, hydrogen will be a +1. When I have hydrogen bonded to metals, these are called hydrides, hydrogen is negatively charged. Why? Because the metal is going to be positively charged. So hydrogen has two choices. One, generally when we see it with, or it's negative with metals. Line 4 looks at oxygen almost always is going to be a -2. Why? Because it is a group 6 nonmetal. It wants to accept 2 electrons to become more stable, have that electron configuration of a noble gas. So here it's a -2, here it's a -2, but here I have hydrogen peroxide. So when I have the peroxide ion, it is actually an O2 with a 2-. So each individual oxygen atom, excuse me, would have a -1 charge. Line 5, I have all these different compounds here with fluorine. Fluorine will always, 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 always be a -1. It will never be anything else. So fluoride is always -1. Line 6 here, I have compounds that have iodine in them. Now, I also note that all of these compounds are neutral. All of these were too. And whatever that, or excuse me, that means that the charges on my individual elements have to all add up to 0. So similar to what we were doing, not electron configurations, and writing out correct chemical formulas for ionic compounds. So potassium is a +1 because it's a group 1 metal. Iodine then has to be a -1 here. So we're following basic rules. But we know that iodine, since it's a group 3 or below nonmetal, it can do different things. It can bond in different ways. So here what I would do is look and I'd say, okay, sodium is +1. My oxygen is normal, so it's a -2. So I go 2 times -2 is -4. Since sodium was +1, I have 4 minus 1, which is 3. Or sorry, a -4 plus a 1 gives me a -3. Therefore, my iodine has to have a +3 charge. So once again, sodium is a +1, oxygen is a -2. 2 times -2 is -4. -4 plus 1 is -3, leaving my iodine to have to cancel out that -3 charge, so it is a +3. Can do the same thing here with my iodine heptafluoride. F, always a -1. I have 7 of them, so 7 times -1 is 7, which then means my iodine has to be a +7. So in looking at neutral compounds, all of your charges have to add up to 0. Which then leads us to our last rule here, which states that all of your charges, if you have a polyatomic ion, has to add up to your overall charge on your molecule. So oxygen's -2. Excuse me. Oxygen's -2. 4 times -2 is -8. -8 plus something has to equal a -2, which means that chromium has to be a +6. And I can repeat the same set of same set of steps for assigning charges in all of these, and I strongly suggest that you do that. So here's some oxidation number rules. I've listed them here. There's also going to be ones in your book, and study the ones that I just told you in the last slide as well. We're going to get plenty of practice with this. So as I was doing before, assign the oxidation numbers to each of the elements in the compound. So we're going to start with the numbers that we know. It's going to be a +1 because it's with other nonmetals. Oxygen is going to be a -2. So I assign those. I see, since I have 2 hydrogens at a +1, 2 times 1 is 2. Oxygen's at a -2, 4 times -2 is a -8. So 2 plus a number all has to add up to 0, which means sulfur has to be a +6. So this is, once again, looking at assigning our charges, making sure we're looking at the periodic table, following those rules, and then simply saying all of these charges have to add up to 0 because overall my molecule is neutral. So here I have ClO3 minus. My minus charge floated away. Don't know about that. So once again, we start with what we know. Oxygen is going to be -2. I have 3 of them. So it's a -6. So something plus -6 has to add up to -1. That would be 5. So +5. 5 minus 6 is -1. I now know the charges, the oxidation numbers on my respective elements. We have to know our oxidation charges because we have to be able to figure out what's being oxidized or reduced. And when we're looking at this, we're saying, what increased its charge? Then it had to be oxidized. What decreased its charge? It had to be reduced. And anytime you're labeling oxidation-reduction reactions, we're always labeling the species on the left-hand side, saying this was oxidized, this was reduced. This is the reducing agent. This is the oxidizing agent. Labeling happens on the left-hand side of the equation. Same thing with acids and bases. So types of redox reactions, we've seen a couple of these earlier. A single displacement. A kicks B out to replace it. So strontium plus water, we're actually going to kick out some of the hydrogen to form strontium hydroxide. That is called a hydrogen displacement. We can also see metal displacements where magnesium replaced titanium in this compound. And lastly, we can see halogen displacement, where chlorine kicked bromine out to form potassium chloride. So in each of these instances, though, we have one thing that is by itself, one thing that is a compound. The single thing will replace the respective charge on the compound that is formed. So here I have a hydrogen with a +2 charge. Well, I have a total, let me start again. Hydrogen has a +1 charge. There are 2 of them, so it's +2. Oxygen has a -2 charge. So the strontium replaced the hydrogen. Here, magnesium is a 0 charge because it's a standalone metal. Here I have titanium. It's a +4 charge. How do I know that? Because chlorine is -1 here. Magnesium replaced titanium. Metal displacement. Chlorine replaced the bromine here, once again, to form potassium chloride. So -1 charge on this side, 0 over here. 0 on this side, -1 over here. If you have a redox reaction, charges have to be changing. Why? Because redox reactions result from a transfer of electrons. Acid-base reactions were a transfer of protons. Another type of redox reaction is combination. A plus B equals C. 2 single things form a new compound. They come together. Here we have aluminum bromide. Aluminum is a standalone metal, so it's 0. Bromine is in its elemental state, so it is 0. Aluminum here is a +3, and bromine is a -1. Aluminum was oxidized, bromine was reduced. Decomposition reaction is just the opposite of a combination. So we start together, but we end apart. One thing breaks down to form 2 things. Potassium chlorate will react in a way to decompose into potassium chloride and oxygen. So here we're not actually breaking down into all of the elements, but we are seeing that once together, now apart. So we can go again and look to see what charges are potentially changing. Potassium is a +1 here. Potassium is a +1 here. Oxygen is a 0. Oxygen is a -2. Chlorine here is a +5. Chlorine here is a -1. So chlorine was reduced. Oxygen was oxidized because it started at a -2 and it ended at a 0. -2 to 0 is an increase in charge, whereas the chlorine that was a +5 to start ended as a -1. Last type of redox reaction is combustion reaction. So anytime we have excuse me, oxygen as a reactant. It is a combustion reaction. So sulfur plus oxygen forms sulfur dioxide. Sulfur starts at a 0, it's by itself. Oxygen, diatomic state, its element, starts as a 0. Oxygen ends as a -2. So sulfur ends as a +4 because 2 times -2 is -4. So +4 has to balance that out. For oxidized and oxygen was reduced. We saw this reaction earlier. Magnesium starts at 0, ends as a +2. Oxygen starts as 0, ends as a -2. Metal was oxidized, non-metal was reduced. And we do tend to see this trend. Metals, why? Because they want to give up their electrons to become stable. So they are generally oxidized. Non-metals want to gain electrons to become more stable, so they are reduced. Notice in both of these combustion reactions, these are also considered combination reactions because I have 2 single things coming together to form one new thing. So here I have a table listed that tells us the activity series for metal. And we want to pay attention to what this is telling us. We have an increasing ease of oxidation. So lithium is the substance that most wants to be oxidized here. And looking at all of these metals. So that means that if lithium is oxidized and it's in a reaction with potassium, potassium would be forced to be reduced. So one thing is going to have more power. One thing is going to have more power as a reducing agent. One substance will have more power as an oxidizing agent. So lithium will be the thing that's oxidized if it's in if it's reacting with any one of these other metals. So the higher you are up on the table, the more power you have to be oxidized, which means that you have the most power to reduce something else. So down here at the bottom with gold, gold is not as likely to be oxidized. Therefore, it does not have the power over anything above it to force that other substance to become reduced. So last part of this chapter is going to deal with balancing oxidation-reduction reactions. So we looked at balancing precipitation reaction. We looked at balancing acid-base reactions. So now onto oxidation-reduction. So first of all, and this is a pretty complicated reaction here, but I have to separate things into their respective groups. And what that means, I'm mixing or I'm collecting like things on one side of the arrow and the other side of the arrow. So for example, I have my MnO4-. I see on this side, I have an Mn, so I would want to group those together. I have an iron 2+, I have an iron 3+. I would want to group those together. And the protons and the water molecules are a result of balancing the equation. So first step, you're going to write separate equations for the oxidation and reduction half reaction. So we're separating our like terms. And really, I just like to call this the ACE method. So once we've separated our whole reaction into 2 half reactions, we're going to balance our atoms, which is the A for ACE. So I'm going to balance all the elements except for hydrogen and oxygen first. I balance oxygen by using water. So for example, if I go back to, well, no, I take that back. If I have permanganate, which is an MnO4- on one side of the equation, and I have no oxygens on the other side of the equation, that means I'm going to have to add 4 water molecules, because by adding 4 water molecules, I'm effectively adding 4 oxygens into the mix. Now, once I've added those waters, I'm also going to have to go back and add in the appropriate number of hydrogens, because every time I add a water molecule, I'm adding 2 hydrogens. So if I've added 4 waters to one side of the equation, I'm going to have to add 8 protons to the other side of the equation. So the next step then, once I have all my atoms balanced, and normal rules of using coefficients to balance equations come into play. So once I've done that, I have to balance the charge by using electrons. So that's the C in the ACE method. Atoms is for A. I have to balance the atoms first. The next thing I balance is the charge, and I do that by adding in an appropriate number of electrons. And the reason why I do this is because for all balanced equations, you have to make sure that if something has a charge on the reactant side, let's say it's +2, on the product side, it has to be +2 as well. Or if everything is neutral, if I have 0 charge on the reactant side, everything has to add up to a 0 charge on the right-hand side, on the product side. So I'm going to add in electrons are negatively charged. So I'm adding electrons in order to make sure that my charges are going to be equal on either side of the arrow. So after I've added in my electrons, I've balanced out my charge. ACE method, ACE. The E stands for electrons. So once I have my electrons added in, I have to make sure that they're equal to each other so that they can then be canceled out. So for example, if I have 2 electrons on the reactant side, I have 4 electrons on the product side, I would have to multiply my 2 electrons on the reactant side by 2. And as I do that, I would have to multiply everything else in that equation by a 2. So I could also have an instance where I have 2 electrons to start and 3 electrons to end. Then I'd be looking for a lowest common multiple. Well, 2 times 3 is 6. So I would respectively multiply each half reaction, the whole half reaction. On my side with 2 electrons, I'd have to multiply everything through by 3. On the side where I have my 3 electrons, I would have to multiply everything through by 2. So now atoms balanced, my charge is balanced, my electrons balanced, reactions back together, and then cancel out identical things. And when we are doing this step, you have to make sure that your electrons are going to cancel. If I don't have an equal number of electrons, I'm not going to have the right balanced reaction. And as always, we're going to check to make sure that things make sense. Our atoms are still balanced and our charges are still balanced. So here's a little table talking about the steps here, writing our half reactions first and then going through the ACE method. Balance your atoms. The way we do this is by adding a specific number of water to one side, excuse me, and a specific number of protons to another. Balance my atoms. I also use coefficients. Then I have to balance my charges. Balancing the charges, I simply add in a specific number of electrons. Once I have my electrons there, I have to actually balance those out. So atoms are balanced, charges are balanced, electrons are balanced. So once I've done that, respectively, to each of my half reactions, I add my reactions together, I cancel out, and check to make sure that what needs to be balanced is balanced. And what needs to be balanced is everything, so. All right, so this was balancing in an acidic solution, and the reason why it's an acidic solution is because H pluses are acids. So if I have protons present, I know that it's an acidic solution. If I want to have a basic solution, then I have to have hydroxide ions present. And once we've balanced our solution in an acidic environment, that's the way that we're going to start. Now what I do is look to see, okay, if I have 8 protons on one side, I'm going to add in 8 hydroxide ions because 8 H pluses plus 8 OH minuses gives me 8 HOHs, which is simply water. So I've done a neutralization. Now, if I add 8 hydroxides to the reactant side, I also have to add them to the product side. So that's where we end up seeing that we can now have a base present in solution. So once we have added the equal number of protons, so once again, if I started with 4 H pluses, I have to add 4 OH minuses. If I have 5, I have to add 5. If I have 2, I have to add 2. Once we do that, we see that we're going to form water. And generally, there's already water in the equation, so we would want to go back and make sure that we are canceling out an appropriate number of water molecules. So here it is. We're forming our water because H plus and OH minus come together, and then we're going to eliminate the number of water molecules that appear on both sides of the equation. And once again, we do that check to make sure that we see that things are all balanced out, atoms and charges. So our basic method for half reactions follows the exact same set of steps as we do in our acid, so we're not doing anything different. We're just basically adding on to what we've already done. I have my ACE method, balance the atoms, then balance the charges, then balance the electrons. Once I've done that, I have my half reactions that I put back together, cancel out identical things. Most often what we will be canceling out is water, potentially protons, and always, always, always the electrons. The electrons going in have to equal the electron because we can't create or destroy electrons in the process of a chemical reaction. So I have my balanced equation. Now I just simply look for how many protons do I have? If I have 3 protons, I have to add 3 hydroxide ions to both sides of the equation. It's just like in math. If you add something to this side, you have to add something on the other side of the equal sign. Once I've added my H plus to 0, I'm forming water. And then I have to eliminate water molecules respectively. So if I added my 3 hydroxide ions to cancel out my 3 protons, I've created 3 water molecules on one side. Let's say I already have a molecule equation. Well, 3 of those would then cancel out, and I'd be left with 2 water molecules. So once we've done that, we always want to go back and make sure that we're all balanced out with atoms and our charges. So in this chapter, we are starting to take a look at 3 common types of reactions. Precipitation, where we have 2 aqueous solutions coming together to form a solid. Within that, we need to be able to predict which of the substances is going to be solid. Once we've done that double switch, that double displacement where everybody's with somebody new now. So once we've assigned what's going to be soluble by writing aqueous and what's going to be insoluble by writing solid, now we're able to write a net ionic equation for that particular reaction, remembering that the ions that are going to show up in that equation have to be the same 2 elements that are in your solid that is formed. Your spectator ions are the aqueous product. So we're going to have to be able to do that, write out these equations, predict the solubility, what's going to be solid, what's going to be aqueous. Precipitation reactions. Then we looked at acid-base reactions. So we have to be able to identify what is the acid, what is the base, by looking at how many protons did you start with, how many protons did you end with, right? If you increased your number of protons, it means you started as a base. If you decreased your number of protons, it means that you started as the acid. Acid-base reactions are also double displacement reactions, except for most often now we see salt being formed. So we're not going to see water being formed in a precipitation reaction. And last but not least, we looked at oxidation-reduction reactions. And these reactions are a transfer of electrons, which means something lost the electrons, substance that was oxidized, and something gained the electrons, the substance that was reduced. And because of this, we're seeing a change in the oxidation state, or simply the charge on respective atoms. And looking at these charges then, we are able to say that what species was oxidized in the reducing agent, and what species was reduced in the oxidizing agent. And then lastly, with these redox reactions, we took a look at specific types: single displacement, combination, decomposition, and combustion. And then we looked at the method for being able to balance out these using the half reaction method. So in terms of what do you need to study for this chapter, you need to familiarize yourselves with precipitation, acid-base, redox reactions, be able to recognize what they are, and identify the specific components of those reactions, as well as being able to balance oxidation-reduction reactions using the half reaction method. So this is what we are doing in this chapter. Make sure you study, read the chapter, and practice the problems. Good luck.